Greetings. My name is Dr. Fuller. I would like to introduce you to the mathematical world around you. Our world is filled with relationships between two or more things, and being able to examine some of these relationships is helpful in daily life and the world of work. A function is a special type of mathematical relationship where each input has exactly one output value. When a function exists, it has useful properties and follows certain rules. Today, my dog Random will help me explain the characteristics of linear functions. Linear functions often begin a student's exploration of mathematical relationships and their representations. The word linear means line like. You can see the word line in linear. In mathematics, a line is special. It has no curves or bends and continues in both directions forever. Therefore, linear functions are relationships between an input value and an output value that can be represented graphically by a line. Graphs of linear functions look like this, and these are graphs of some nonlinear functions. A relationship exists between the day of the month and the total amount of food given to Random. For example, each day she gets a good girl stick. We say the number of good girl sticks eaten is a function of the number of days passed in the month. This means as the number of days changes, the number of good girl sticks changes. This also implies that the number of good girl sticks eaten depends on the number of days passed. The idea that one value depends on another leads to some vocabulary. The number of days passed is the independent variable. It is also known as the input variable and x in standard form. The input variable takes in values from the domain. The domain is what we call all the possible values for the input variable. In the case of Random's monthly treats, the domain represents the possible values that can be put into the function. The only numbers that make sense are the whole numbers from 0 to 31. We can say the domain is all the whole numbers greater than or equal to 0, but less than or equal to 31. The number of good girl sticks eaten depends on the day. Therefore, it is the dependent variable. It is also known as the output variable and y in standard form. The output variable gets its values from the range. The range is all the possible values for the output variable. With Random, the fewest good girl treats she can have at any point in the month is 0. The most she could have eaten is 31. One stick per day for a month with 31 days. And she would never eat part of a stick. In this case, the range is any whole number greater than or equal to 0 and less than or equal to 31. Notice the output variable is 1 to 1 for the relationship between the number of days passed and the number of good girl sticks eaten. For each day of the month, there is only one total number of good girl sticks eaten. In this situation, there's only one possible answer for each input. This one-to-one relationship is a defining characteristics of functions. You might remember working with direct variation or proportional relationships. When one value increases, the other value increases in direct variation relationships. Direct variation is represented by the equation y equals kx, where k is the constant of proportionality. The number of good girl sticks eaten by Random is represented by the function y equals x. In this case, the constant of proportionality is 1 because Random gets one stick per day. If we create a table, select input values, and calculate output values, we get something like this. Plotting these as ordered pairs, we get this graph. This graph represents the function y equals x, where each output is equal to its input. This is the base linear function. Sometimes I must buy different treats for random. She likes Dogo cookies. They are smaller than Good Girl sticks, so she gets more. This table represents the number of Dogo cookies she eats daily if she eats 3 per day. Next, I will plot these points on the previous graph. Notice the steepness of the new line. As you increase the input by 1, the output increases by 3. The new line is much steeper than the original line. The line's steepness is called its slope, a value representing the rate of change. The slope is always the same between any 2 points in linear functions. This is not true for nonlinear functions. The slope is the ratio between the change in the output to the change in the input. To calculate the slope, start by selecting any 2 points. Starting with the top of the ratio, subtract the two output values. For the bottom of the ratio, subtract the input values in the same order. Then, simplify the ratio to get the slope. For Dogo cookies, the slope is 3. Wait, the slope is the same as the number of Dogo cookies she ate daily? But then that makes sense because the slope is the same thing as the rate of change and the unit rate. The unit rate is 3 cookies per day. Therefore, so is the slope. This gives the equation y equals 3x, where we multiply the number of days by 3 to get the number of treats eaten. Notice the differences between the functions of Good Girl sticks and Dogo cookies. The coefficient in front of x shows the slope and reflects a slope of 1 versus 3. Now look at the tables and the graphs. Both show that the number of Dogo cookies eaten is greater than Good Girl sticks. The coefficient in the function, the rate of change in the table, and the steepness of the line in the graph all show the same idea of slope. Okay, so I need to be honest. The day Dogo cookies arrive, Random gets so excited, I have to give her 5. This means she eats 5 right away and still gets 3 each day of the month. This relationship can be seen in this table. Notice that the slope is still 3. The rate of change is the same as before. Random still eats 3 cookies per day. However, the values have all increased by 5, representing the initial eating of 5 cookies. Plotting the points on the previous graph gives this new line. The steepness of the new line is the same as the previous line. However, its position has shifted up 5 units. The shift in position seen in the graph and the increased values in the table can be represented by the function y equals 3x plus 5. In mathematics, we call the added constant, in this case the plus 5, the y-intercept. It represents where the function's graph crosses the y-axis, where the input equals 0. A function in the form y equals mx plus b is said to be in slope-intercept form, where m is the slope and b is the y-intercept. Writing linear functions in slope-intercept form is helpful because we can read the slope and y-intercept from the equation and can sketch a graph using only this information. A third type of goodie that Random likes are mini sausages. She eats 1 when they first arrive and then 4 per day. The function representing the number of sausages eaten is y equals 4x plus 1. Its slope is 4, which is greater than the function representing Dogo cookies. Its y-intercept is 1, which is less than the function representing Dogo cookies. If we were to graph it, we should see that the line is steeper, but crosses the y-intercept closer to 0 than the line representing Dogo cookies. Instead of creating a table, calculating values, and plotting points, I will use the slope-intercept form to graph the function. I will plot this function on the previous graph. It takes 2 points to create a line. Begin by plotting the y-intercept. Move up or down along the y-axis to plot the first point. To get the second point, I use the slope. The slope is a ratio in the change in y over the change in x. Writing the slope as a fraction, I get 4 over 1. This means the next point on the graph is up 4 because the slope is positive and the numerator is 4, and then right 1 because the denominator is 1. Now that I have 2 points, I can draw a line through them. This graph shows what we expected. The function for sausages has a steeper line passing through the y-axis closer to 0 than the line for dogo cookies. The functions, tables, and graphs all tell us information about the situation. If we have one representation, we can create the others. Linear functions written in slope-intercept form allow us to understand certain aspects of the function. Slope-intercept form is a quick way of graphing as well. There are two main types of kibble random likes. They cost the same, so I want to know which bag lasts longer. Unfortunately, she is supposed to eat a different amount of each food, so I cannot just look at the size of the bags. One bag is 10 pounds. She eats 1/4 of a pound per day. This can be represented by the equation y equals 10 minus 1/4 x, with x being the day and y being the pounds of kibble left in the bag. The other kind of kibble comes in a 5 kilogram bag. She eats 1/10 of a kilogram per day. Y equals 5 minus 1/10 x represents this function. Which bag is a better buy because it lasts longer? What else can you tell from the math? To work with the first function, y equals 10 minus 1/4 x, I convert it to slope-intercept form. I rearrange the terms in the equation using the commutative property of addition. Now I can read the slope and y-intercepts out of the equation. The slope is negative 1/4 and the y-intercept is 10. This matches the situation where the bag starts at 10 pounds, the y-intercept, and decreases each day by 1/4 of a pound, the slope. The second function also requires rearranging to y equals negative 1/10 x plus 5. The slope is negative 1/10 and can be written as the fraction negative 1 over 10. The y-intercept is 5. Again, this aligns with the situation. The bag starts with 5 kilograms and is reduced by 1/10 of a kilogram daily. We can see that the first kibble's y-intercept of 10 is twice as large as the second kibble's y-intercept of 5. The slope of the first kibble decreases faster than the second, 1/4 compared to 1/10. But let's look at the graphs. Using slope-intercept form to graph the function y equals negative 1/4 x plus 10, I plot the y-intercept, positive 10. Then I use the slope, negative 1 over 4, to generate the next point. This slope means the next point is down 1 and to the right 4. Plotting a second point and then drawing a line gives this purple graph. For the second function, y equals negative 1/10 x plus 5, again I start with the y-intercept. I plot the point 0, comma 5. Next, use the slope of negative 1 over 10 for the second point. I go down 1 and to the right 10 from the y-intercept. Finally, drawing a line through the 2 points creates this graph in orange. Looking at the two graphs, you can see the purple line representing the first kibble crosses the x-axis at day 40. This means the bag of food will be empty on day 40. The orange line represents the second kibble. It crosses the x-axis on day 50, meaning the second type of kibble lasts longer. From the functions, I know a few things. The y-intercept of both functions represents the bag when full, either 10 pounds or 5 kilograms. Both slopes are negative because the amount of kibble in each bag decreases over time. Also, the absolute value of each slope is the unit rate, the amount of kibble eaten per day. From the graphs, I can read the x-intercepts, which represents the day when the bag is empty. I can also see the slope of the line representing the first kibble is steeper and decreases more rapidly than the other kibble. Finally, from the situation and the math, I know the domains and ranges of both functions. These represent the minimum and maximum amounts of food at any given time, and the possible days the bag will exist in my house. Using graphs with the same x axis allowed us to compare the two products, even though they were measured in different units and random ate different amounts. Concepts related to functions, equations, and graphs allow us to understand and use some of the relationships between the variables. In my mathematical world, I have one little problem. The veterinarian said Random is getting fat. I must adjust her diet to ensure she is a healthy puppy. The following graphs represent some relationships between Random's information. Which relationship is linear? Which does not represent a function? I found some large biscuits that Random likes. When I first bring them home, I give Random one biscuit. Then she gets one biscuit every 3 days, as shown in the table. If I follow this pattern for a month with 31 days, what are the domain and range? What is the y-intercept and what does it represent? What is the slope and what does it represent? A different brand of low-cal biscuit is smaller. When the box first arrives, I give Random 3 cookies. As represented in this table, she then eats 2 cookies each day for a month. What function represents this situation? How does the function compare to the function y equals 3x plus 5, representing Dogo cookies? Random can eat 700 calories per day. One diet has her eat a reasonable amount of food, but allows her to eat a few smaller treats during the day. This table represents the additional treats and calories she can eat for this diet. What function represents the calorie consumption based on this diet? A different diet emphasizes a snack based approach to weight loss. Random gets one small meal, then several snacks throughout the day. The calories for this diet are represented in this table. What function represents the calories eaten for this diet? What information can you determine from the functions and graphs representing the two diet situations? Take a look, and you will see a mathematical world around you filled with relationships, functions, and linear functions. Terminology like domain and range provides us language to describe attributes of a function and is essential for accurate communication. Understanding how to work with different representations makes functions powerful tools that allow us to build the future.